Nobody.
All right. Hi, everyone. Thank you for coming to this talk on image and video processing in Java. Our speaker tonight is Jim Carroll, longtime Philly Jug member and many-time presenter. He is the CTO of Kognition, and excited to share. It's hard to see from people on the live stream. It's a very complicated setup here, which took hours to get going. So we're really excited to see what he has to share about his recent work. Jim, the floor is yours.
All right. We're going to be going through a lot of code, so, but let me make sure I actually have that turned off. All right. I hope this doesn't start too basic, because I do kind of start from the beginning and lay the groundwork. Feel free to interrupt me at any time. We can make this as interactive as you want. I have no idea how long this is going to go. It might go too long. It might be done in 10 minutes. So we'll see. So anyway, who knows what OpenCV is already? Nobody? Oh, good. Okay. OpenCV is probably the most popular computer vision library. It's been around for a really long time. It's written in C++. I believe it's written in C++ and has C bindings, not the other way around. And it's has Python bindings, which is most popular use, and Java bindings. So anyway, we're going to start by even talking about what an image is. So this might be too basic, but so for our purposes, we're going to define an image as a two-dimensional array of pixels. A pixel is a picture element. That's what the word means. And a pixel is a representation of a color at a particular point in an image. Oh, sorry, my camera is my okay. So colors usually represent as a three-dimensional value. For almost all computer vision that I know of, computer vision algorithms or computer vision systems that I know of, it uses additive primary colors like RGB. Don't know of any that work in another color space, but it's it's possible. So OpenCV is typically has image representations in the color is 3-channel RGB is a color image. If it's a grayscale image, it's probably 1 channel. So anyway, there's a lot of other representations. CMY is cyan, magenta, and yellow. That would be a subtractive primary color system. CMYK is what printers use. K is black. And YUV, I might talk about later because it is important for video compression. So I don't know if you know. Does anyone know what YUV is?
It's like luminosity and
yep.
Something else. Chrominance, right?
Yeah. Chrominance, yes. Yeah. So there's actually it's pretty interesting. It's developed in the 40s, I think, for color television. And what they did is they wanted to broadcast the color signal on the same equipment, not the same equipment, but they wanted to be able to receive it on black and white television. So they wanted the signal to be redundant. So he needed to put the color information somewhere. So they broke the color down into intensity, which is the black and white picture, and then 2 degrees of color. Yeah, and that's what the UV is. And the reason they could get away with that is because the human eye perceives intensity much more finely than it perceives color. So you could get away with less bandwidth to. Yeah. So, and they still use that in digital video, which we'll get into. Anyway, so an image is typically 3 channels if it's color. So OpenCV represents an image in an object called a mat. I actually don't know. I think it just means matrix, but it's an OpenCV mat. It's an n-dimensional interleaved array. Interleaved meaning the values that represent 1 pixel are all right next to each other in memory. So if it's red, green, blue, the red, green, blue values are right next to each other in memory. It's usually packed, meaning it's 1 continuous buffer. Not always, though. And so it's usually 2 dimensions, but you can have multi-dimensional. You can have a multi-dimensional map, but it's usually 2 dimensions. Obviously, if it's an image. And so you would say a color image is 2 dimensions with 3 channels.
Is
Yes?
it laid out by scan line or by row or by column?
It's row major order. So it's row by column by channel. Right.
Okay.
So the bytes that represent 1 pixel, the different channels are right next to each other. That's the way that mats represent. That's the way when you load an image into OpenCV into a mat. That's the way it's laid out.
So it's kind of representing the scan lines.
Yes.
Is that a standard or is that just convenient?
If you look at Java,
Anything goes.
if you look at Java images, they will load anything. So they'll load planar images where the red, green, and blue channels are completely separate from each other into different buffers. Those are not that's non-interleaved, for example. So you could have a non-interleaved packed array where you have 1 continuous buffer, but you have all the reds first, and then you have all the greens first, and then you have all the blues first. So there's lots and lots and lots of different ways to represent the stuff. But in OpenCV, for the purposes of most computer vision algorithms, and even all the new deep learning stuff, I don't know of any that don't operate on a 3-channel color image. Now, they don't always operate on a packed continuous array. Sometimes you have to separate the channels out before you give it to the network, but most of them are. Okay. So OpenCV is an unbelievably extensive library of routines that you can call on mats. There's all the arithmetic stuff you would want to do, lots and lots of image processing. What you really don't want to do is probably go in and manipulate the pixels yourself. So you just treat the mat as a matrix, and you just do full operations on the whole thing, typically. So, and because it's optimized, so you're not going to write it faster than they've written it, than Intel wrote it. Well, Intel, oh, by the way, Intel started OpenCV, open sourced it many, many years ago, and just in the last year, I think, took it back. Maybe 2 years ago, took it back. So it's now under the control of Intel. It's still open source, but Intel is now basically in control of everything. So all their NVIDIA stuff is kind of stagnated. All right. So a quick code example. This is a simple load image read of a test image into memory. Print it and then display the image. This is all OpenCV. There's none of my code is in this. No custom code. No custom libraries, I should say. Obviously, this is my code. Pure OpenCV, and it's pretty straightforward. Okay. Now I actually have the code commented out here. I was going to actually type it in, but I'm like, I don't want to figure this out. I mean, I could figure it out, but it just takes too long. So, just to give you an example of the kinds of things you can do, this is a edge detection. So this is a very traditional. I actually thought it was older. I looked up when it was created, a candy edge detection. It was apparently published in 1986. I actually thought it was older than that because I was using this in 1988. So it's considered a classical computer vision algorithm. So it's not all the not with the neat neural network stuff or anything like that. But here's an example. Take a mat that I loaded. I'm going to blur it.
So is this manipulating in place?
Yes, this is source destination. Source is image. So I'm saying blur the image and write it back into the same image. Size is the size of the kernel for the blur. So it's basically blurring over an 11 by 11 neighborhood. the image spatially. So this is a Gaussian blur. So if how it works is it takes a Gaussian set of weights centered around every pixel and averages all the pixels in the neighborhood weighted that way. So the farther away they are, the less they contribute, and that becomes the new value. Then it moves over, goes to the next one. That's what a Gaussian blur is.
So why 11 by 11 seems like a pretty large neighborhood?
Yeah, because I played with this just to get decent results on the final edge detection. So yeah, it is pretty big, and you can see it's pretty blurry as a result, right? So this is a gradient calculation, which isn't really that complicated, but it's a char or Sobel. There's two different ones. Char is really good at if you're trying to calculate the gradient in a real small area. Since I just blurred it, now I can just calculate the gradient over a small area instead of considering a lot of it. And the idea here is that as pixels rapidly change intensity in the x direction, as you move in the x direction, you get a high value in the gradient. And then as pixels change in the y direction, you get a high value in the y direction gradient. So this actually calculates the gradient in two different directions.
That invisible, can you represent that
Yep.
as a visible image?
Yep. So the other thing to note here is that, so let me just talk about this quickly. When I print the mat, it gives me like what's like the metadata for the mat. So it gives me the rows, columns, and the type. And the type is it's always not always packed, but it's always interleaved. So this is each channel, it's an 8-bit unsigned integer, 3-channel. Is continuous means it's packed basically, which means it's not broken. So it's everything's in one continuous buffer. So yeah, if you want to see the gradient in the x direction, so as you move in the x direction, wherever there's a higher, more rapid change, you'll get a higher intensity for that particular channel.
What's the resolution of it?
675 by 1200. Yeah. So and actually, so since you're taking the gradient, you're doing a subtraction. So the final number, if the numbers you're subtracting can go from 0 to 256 or 255, then the results could be from less than 0 to greater than 255. So that's why if you notice, I told it to put the image in a 16-bit signed result. So if I print I probably should have done this. But if I print this out, you notice the result, the actual gradient is 16-bit signed 3-channel. So, okay. I got an argument with ChatGPT over this, over whether I needed to take the absolute value, but this is, I mean, you could see you can operate on entire mats with a single operation. And if you pass, typically, this is a lot of these operations work where you pass it a mat and a scalar, and it'll do the operation between every pixel and the scalar, or you can pass 2 mats and it'll do the same operation pixel by pixel.
So it's basically just taking the absolute value of each pixel?
Yep.
Because it's going against a scalar of 0.
Yep.
Okay.
Yep.
And ChatGPT didn't tell you that?
No, I didn't. Because canny operation needs both needs the full gradient. It needs the direction, and so the way canny works is once you take the gradient. Imagine the gradient image where the peaks. They have these mountain ranges, right? And the peaks are the places where intensities are changing the fastest. The way canny works is it finds the peak, and then it follows the peak to try to find the edge, because that should represent an edge. right? And so the reason there's two values passed to Canny is because these are two thresholds, and it does a hysteresis. So anything above the top threshold is considered an edge, wherever the peak of that edge is. And then it follows the edge, and the edge has to drop below the second threshold before it considers it not an edge anymore. So actually, I didn't think I was going to talk about the particular algorithm. The particular is the algorithm, but so let me actually get like this. There we go. All right. So in memory, the way this is represented in Java, you have a class that has a single long. And really what it is the address of a native C++ object that has that is the mat. That does not contain the pixel data either. That contains a reference to the pixel data. And there's a reference count on this pixel data. Right. So you can have multiple mats that point to the same pixel data. They'll be reference counted. When the last mat goes out, it's deleted on the C++ side. It cleans up the buffer. On the OpenCV Java side, the finalize deletes the C++ object. The last C++ object holding a reference to the pixel data cleans up the pixel data. Anyone see a problem with this?
Well, other than, you might have the C++ data disappear and still have native object at the value.
No, because the finalize, if you not until the finalize is called. So the garbage collector has to read this before the C++ object will go away. This is actually created by the Java side through JNI, right? So its only purpose is to be a reference from this thing. But it's not actually going to be deleted until the finalize gets. So the biggest problem with this is, suppose we have a 4K image. Java sees 8 bytes, but it's nearly 30 megabytes in memory. So if you're decoding video at 60 frames a second, 4K video at 60 frames a second, you have 60 30 megabyte chunks of data a second. This works almost 90% of the time. If you do anything with that mat that moves it from the earliest stage of the garbage collector, this runs out of memory in seconds. So, and they give you no control in the Java API over actually deleting that. You have no control over that. So we extended it. So PileCV4J is an open source library that is older than our company is, but basically our company is now kind of maintaining it. But it has a bunch of different components. There's libimage is one of them, and the purpose of libimage really is to extend OpenCV to make it more usable in production systems on the Java side. I mean, it's perfectly usable in Python and it's perfectly usable in C++. But this is a problem in video systems. I ran into this repeatedly, and rather than try to tune a garbage collector or try to make sure that the mat never leaves the earliest generation of the garbage collection, just this turns it into a mat into a Java resource. So let's go to the second example.
If you aren't pulling the mat onto the Java heap.
No.
Okay.
Jim, your friend Mike has a question on the chat. I don't know if you can see it on your screen there.
I cannot, but can you relay it?
Hey, Jim, it's Mike. How is the removal of finalize with Project Panama going to impact PileCV4J? And can I log back into my work laptop you gave me to update it?
It's that, Mike.
Yeah.
I have no idea. Actually, they're gonna remove finalize.
Yeah.
What you really got to do is ask what OpenCV, the Java bindings for OpenCV are going to do. They might move to this. I think it's a stupid idea to remove finalize, but whatever. We use it for error detection all over the place. Like if you forget, since I do a lot of stuff with native resources, I override finalize to error check that it's been closed correctly. So anyway,
Finalize exists to save you sloppy programmers.
yeah, I guess.
I think there's cases where finalize actually isn't called at all.
We can get into that over again.
But don't rely on finalize.
I'm pretty sure what OpenCV is going to have to do then is make a mat a resource. So some of the stuff might be superfluous at that point. We had to do it because we would. It's really was very idiosyncratic. It would work fine. Then you would change one line of code that didn't seem like it would affect anything, and all of a sudden, it wouldn't garbage collect them fast enough. Oh, it's only 8 bytes. I don't have to worry about that right now. Off heap memory. So I read an article on off heap memory once.
Well, they're probably doing all of their allocation in C, and
Yeah. So this is not quite fitting. Let me see if I can. So this is the exact same code, except for all of the resources now, including an image display, which is part of PileCV4J, is now a Java resource. And so you create them inside of the try with resource. And then obviously when that closes, everything gets cleaned up. And I did not do that by pulling the image into the Java heap. I did it by writing C code that extends the mat. Actually, doesn't even extend the mat. It just does what you can do on the C side that you can't do on the Java side with code. It's exactly the same code, except for CV mat is a OpenCV mat. It doesn't. I mean, it's inherited from it. So anything that will take a mat will take a CV mat. Except in this case, it actually will close it. Let me. So there you go. Okay, we just talked about this, but actually I do override the finalize to make sure that you actually close the resource and aren't leaking it, and you'll get warnings if you leaked it. As a matter of fact, if you set a particular environment variable, it will not only give you warnings, but it will tell you where it was instantiated when it in the finalize. It'll say, hey, you leaked the mat that was originally instantiated and give you the full stack trace. Also, there's utilities for managing raw mats. So there are routines that return mats from OpenCV, and you want to be able to close them. There's a closer object, add the mat to, and basically delete them in reverse order. There's also a move, which follows the C++ rules. Familiar with those? Probably nobody. Okay. Does anyone know what an augment is? No. Okay. The way move basically is it just creates, it just basically moves who's responsible for the underlying resources. Right. So what you don't want to do is use the mat that has to move after, because it's no longer managing those. It's no longer pointing to the underlying C++ mat. Also, if you use PileCV4J, you get automatic management of the underlying binaries, including the OpenCV libraries themselves. So I don't know if this is a good idea or a bad idea. It works for us right now, but I'm in control of compiling those. So if you wanted to compile OpenCV differently, this might actually be a problem. But the way this works right now is you take the native bindings for PileCV4J, which are very small, and transitively, this pulls in OpenCV itself. So you don't have to install OpenCV on your system first. You do have to initialize it, somewhere. You actually don't, this is somewhat optional. If you use CVMATs only, you don't need to do this because the first time the CVMAT class is loaded, it'll do this. But if you use OpenCV and haven't done this, then you'll get a bunch of unresolved errors. So,
Jim, can I back up with a question from a few minutes ago?
sure.
This is from Sham. Is there any limitation of any image types, JPEGs, GIF, TIFF, in image processing, or can it process only certain types?
So the images are always decoded before. So those are encodings of images. So when you read those images, there's going to be a decoding step that takes place in the underlying library. And OpenCV has a ton of decoders. So OpenCV can open almost most images. PileCV4J can open a lot more because it merges OpenCV with ImageIO. There's a fallback. So if OpenCV fails to open it, it falls back to trying to open it with ImageIO. And ImageIO is a plugin architecture, so you could plug in different, lots of different image codecs. So ultimately, what happens is, no matter what the format is, as long as it can decode it, it ends up in a packed, interleaved array in memory. So, and then you can do whatever you want with it.
So talking about this afterwards.
Oh, sure. Okay, this is another thing that you can do with PileCV4J that you cannot do with OpenCV. You can get direct pixel access. Direct bulk pixel access. You can get direct pixel access in a sense, but with this you can get direct bulk pixel access. If you call this and pass a lambda that takes a byte buffer, it will give you a byte buffer that's a direct reference to the external memory. Then you can do what you want with it. If you want to return something, you just call bulk access up, and then whatever you return ends up returned from here. You could be cheeky and return the byte buffer itself, but then I'm not going to guarantee that memory is going to stay there when you go to use it. But, so if you could actually use it within the scope of this call, it's not going to get ripped out from underneath you. If you return the byte buffer and try to use it later, you don't know if the image is still got the if the memory's still there.
It's not going to copy it into the Java heap, you're saying? So
does
if
not
you
copy
return
into the Java
byte buffer,
It does not copy. It's a direct byte buffer. It does not copy into the Java heap. So, an example.
Someone like Keith be trusted to do something like that?
We have to keep people away from direct access to the machine, but so here's an example. This is I read in an image. I have two displays. Read in an image, display the image before I modify it. Get direct access to the pixels. I'm going to iterate over the entire buffer by threes. So every 3 bytes, I'm going to delete the first and second byte. I'm going to set them to 0. So what's that going to do?
Get rid of all of one channel.
It's going to get rid of all but one channel. Right. So I should see the picture. Then I should get rid of all but one channel. Should be blue, right? Then I should basically display a blue image. No, let me do that here.
That's definitely not blue.
Definitely not blue. And it's all definitely not the original either. So, I did mention OpenCV was created by Intel, right? The purveyors of Little Indian.
Yes.
Yes. So while the entire world, including HTML developers, use RGB, OpenCV uses BGR. So yes, and so the other problem here is that neither PileCV4J nor OpenCV will do the most optimal thing it can do. So in this case, when you display the image, there is a shallow copy of the image that's being displayed. So if there's a race condition here, I pass it to display the image. Then I change it. But by the time it displays the image, it's only a shallow copy. There's only one copy of the pixel data. Right? So that's why both of them ended up changed. So Another thing, let me kill this. Oh, because another thing PileCV4J adds is the ability to explicitly do a shallow copy or a deep copy, which you can do with OpenCV, but there's no call called shallow copy. You have to kind of know the semantics of clone versus copy to, and some of them work differently depending on whether or not the data is already allocated for the image. But PileCV4J makes it easier. You can explicitly do a shallow copy, in which case you don't get a reference to the same C object. You still get two C objects, but the image data, you get one copy of the image data. So if I do a shallow copy and make a change to the copy, and then I display the image, you'll see the change.
Can we get one of the functional people to say that mutability is the root of all evil?
Yeah. Yeah. Or you could do a deep copy, in which case you'll get a copy of both the C++ native object as well as the underlying buffer. I already mentioned a couple more things that PileCV adds to OpenCV, more robust image codecs. There's a couple more algorithms which are somewhat ad hoc, which is kind of the reason it's called PileCV4J, is because when it started, it was really literally just a bunch of ad hoc additions to stuff that didn't really have much of a rhyme or reason. There's a generalized Hub transform, which doesn't actually exist in OpenCV. There's also the image display you saw. That's actually an abstraction with a few different implementations. One of them is built on SWT. I wouldn't use any of these to build a fat client with, like a production app, but it's good for just trying stuff out, trying to see stuff while you're playing the code. What's a video? What time is it? How are we doing for time?
7:15.
Okay, so if you guys don't ask me more questions, we're going to be done quicker than.
The last questions.
All right, I'm about halfway through. I guess is that good time? All right. No, go ahead. Excuse me. So video is basically a sequence of images displayed at a given rate. OpenCV has built in a video capture, so you can actually read from the video file frames and do whatever you want with them in OpenCV. This is a mix of OpenCV and PileCV4J. Obviously, as the image display, which is PileCV4J, is CV Mat, but this video capture is pure OpenCV, and this basically just reads a frame and updates the display. Just reads a frame off the stream and updates the display. So I can run this. I don't know how impressive it's going to be, but I hope it works. There you go. It's just reading the frames from that. Pure OpenCV. Well, at least the video part of it's pure OpenCV. My presentation. Sorry, I must close. I need to escape. Okay, just threw this in here. This is actually from the OpenCV documentation. It's kind of the architecture of their video. I guess the only other thing to really note is that they have multiple backends. When I get into the PileCV4J video side, it's all built on FFMpeg. So it's good. If all you need to do is get frames from a video, it works fine. But if you want to do something more sophisticated with video in general, it's not that great. So this is a great kind of rule of thumb. I wouldn't call it. It's not hard and fast, but this is a really good way to look at digital video. The way digital video is created, processed. I mean, how many people know like an MP4 file is, like internally, like what it is? So, so anyway, there's multiple layers in digital video. There's the protocol layer. You can have it on a file system. You can serve it with HTTP. You can go right from here to here, right? If you take an MP4 file and you put a web server in front of it, you're serving. You're basically going from here to here, serving you're changing it from a file to HTTP access. There's the format layer or container layer. You'll hear people talk about containers in digital video. They're containers that hold typically multiple streams of data. And the streams are usually interleaved. So you'll have audio and you'll have video streams, and they'll be interleaved, so that as you move through the file or move through the source, you'll get different pieces of different streams as you move through it. On the input side, this is in reading it, and then on the output side, if you're creating one of these things, you have a demultiplexer on the input side to separate all the streams. So you have a multiplexer on the output side to basically take all the streams and put them back into the container. How are they going to be interleaved back into the container, and then either into a file or served from HTTP? You have the codec layer, which is this is a video stream or an audio stream for that matter. How is it encoded? Obviously, it's going to be compressed. It's going to be encoded with some particular algorithm. So you need to be able to decode it in order to get the actual raw pixels out of it. And then if you want to actually create video, you need to be able to re-encode it or encode it before you multiplex it, before you put it up to an output file, right? OpenCV, raw OpenCV, you can work from here, but that's it. You can't work in here. So that video capture is basically, you're here, and OpenCV is taking care of this part of the chain for you. You point it to an input, camera, file, whatever, and you live over here.
Well, it's like FFMpeg that's doing those first two things, right?
In OpenCV, they plug a different plugin for backends, right? For PileCV4J, this is the PileCV4J version of that. It's all compiled against FFMpeg. This is Java on top of FFMpeg. And this is now from libimage, now it's libFFMpeg. So, PileCV4J libFFMpeg has a media context. This represents kind of that whole input side of the processing chain of the digital video architecture. And this is one of the easiest ways to use this. I'm basically saying, create me a media context from this source, and I want to process video frames, pass me the frames, and all I'm going to do is update the display. Right? So, oh, did I miss it? And you get exactly what you expected then.
We're all members of the Blue Man.
And so, OpenCV,
RGB versus BGR.
yes, but OpenCV's video codec, video capture device, video capture code is matched with OpenCV's output, so you don't have to worry about it, right? It's BGR, and it takes a BGR and it displays a BGR. PileCV4J, if it doesn't have to do any work, won't do work. It doesn't want to tax the CPU. If it does have to do work anyway, because most digital video comes in YUV, like we mentioned earlier, if it has to convert it anyway, it's going to choose RGB. And the reason is because nobody uses BGR except OpenCV. So in my work, I don't want to translate it again. So when I'm passing it to external systems, everyone expects it in RGB. So,
It's
but
kind of funny that people with green haven't been modified.
yeah, there you go. Yeah.
but does it also convert our speech to Navi?
Yeah, so it doesn't do audio, at least not at the decoded step. It will remux audio, but it won't do audio. But it does have a few helpers here. So if you just say you prefer BGR, because you're only going to be using OpenCV, then yeah.
What are you rendering this with? Is this, I mean, it's not swing, but how is it?
No, I almost did a swing. So it's this is actually using OpenCV's the high GUI I had in the first one.
Okay.
This is actually an abstraction, but it has multiple implementations. But one of them is OpenCV's high GUI, and that's the default one. So it's the same as OpenCV's high GUI. There is a SWT one, so the Eclipse library, which is a multi-platform library. And I almost did a swing implementation, but it was like too tedious, and I didn't feel like doing it. So I already have like 3 implementations of it. So if you want to do a swing one, it's it's pluggable. Like the display is pluggable.
Java.
Yeah.
Whatever.
So yeah, I mean, it's just basically taking them. It expects a mat. It just displays it. Really, this is really just a suggestion for BGR, because it has to decode the images anyway in video, and if it has to convert it, to BGR or RGB, you could say I prefer BGR. Otherwise, it's going to opt for RGB. If it doesn't have to convert it because it's already one of those, like it's potentially, I don't know any video streams that I'm sure result in a decode after the decode is already in that correct color space. Maybe MJPEG. If it's already there, it's not going to do anything. It's just going to give it to you. And the only difference, here is that this is a CV mat, but it's a video frame which inherits from CV mat. So it really has one additional piece of information on it, which is whether or not this is BGR or RGB. So I can ask, is this frame BGR or RGB? Or I can actually ask it to give me the other one. I can ask it to give me one or the other. So another way I could have done this would have been to say, well, let's just do this with a leak, because I don't feel like writing too much code. And I can tell whether or not I want to guarantee deep copy, but I don't care. This will work too, and it will leak. What's that?
It doesn't have the lag of the previous one.
It doesn't have the lag of
The last,
yeah, the video the OpenCV one. I'm not sure what the default back end is, but there's definitely a bit of a lag on it. Yeah, this built on FFMpeg directly seems to be much less laggy. See, look. So, okay. Oh, it's only 2 of them. Or 3 of them.
Yeah, you're running a lot.
How much RAM do you have on this machine?
I don't even know. I'm not even sure, actually. It's got a 4 gigabyte GPU in it. So it's pretty meager, but it works. So another thing you can do is remux. So if you can get away with not decoding, see, the most expensive operation in this pipeline is always going to be encoding. The next most expensive operation is decoding, but it's much, much less than encoding. But if you can get away with not encoding or not decoding, you can do a much more optimal processing. So if I have video and all I want to do is at least put it out in a different container in a different media, then I can do this with the lib FFMpeg. I can't do this with OpenCV. So here's an example where I'm writing an AVI file from the camera. Now the stream doesn't end. So I have to kill it sometime in order to play the video file, which actually is a problem for some container formats, but not for AVI. So, where did I write that to? Yeah. And that's really computationally inexpensive because it's not decoding it. It's just unbundling the stream of data and putting it back in a different container. So we went from an MP4. I'm sorry, went from an RTSP. Went from an RTSP live stream to basically.
So if you're writing tools to do translations to different formats, you don't do the other levels of processing.
Yeah, exactly. You could do both, and we do both. So, for example, we will be decoding the frames, but at the same time, we'll be repurposing the live feed. So we'll send the live feed to a video, like a video server. So connect the video server, send the live stream to it, so that an application can, while it's processing the video, you can actually see the camera through an application also. So, and you can do that in Java with this. You do both of those things. So I could remux and do process the frames.
But then API doesn't have a particular encoding required. It's just how it's packaged.
So RTSP is H264. This is set up as H264. I could actually set it as MJPEG. So you could bring back the layers up. So the codec is H264.
Yeah.
AVI supports H264. So because I know my stream, if I know my stream at this point, my video stream at this point is H264, I don't need to decode it and re-encode it to get it into an API file. I could just basically take the stream, raw stream, and just re-multiplex it into, a new container. If there was an audio stream and AVI also supported the audio stream, this would work. If it didn't support the audio stream, then you'd end up with errors trying to put the audio stream in the file. So,
I have questions about how audio streams and video streams mix together in a sequential file when the bit rates for the two are entirely different. The frame rate is 60 hertz. The audio bit rate is way
I can explain that if you want.
It might not be inappropriate. Maybe it.
Sure. Well, yeah, I could explain. Let me see if I can do it quickly. There's each of these streams has internally what they call a time base, and it's a rational. So 1/90,000, for example, is a typical video time base. Well, the audio stream also has one, like 1/40,000. And you write packets interleaved in the container. The point of the container, that's why it's called a multiplexer. The point of the container is to interleave the packets into the container so that when it reads them out and separates them again, the player takes the timestamps in terms of that time base and makes sure they're all synced and played back together. It doesn't matter whether it gets 3 audio packets between every video packet. Or
I see.
So the demultiplexer will separate the streams, and then the player will follow the time base. So each packet corresponds to its stream's time base, and so it knows exactly when it has to.
So the interleave doesn't mean it's going one then the other, one then the other. It's going one, then 3 of the other,
Yes.
one.
Yes. Yep. And they're in terms of their separate time bases. So the streams don't have to be, the streams inside of the same container don't typically have to be on the same time. They typically aren't on the same time base. The audio time bases are not necessarily the same as video time bases. So,
And whose job is it to make sure, is it the player or the muxer?
That's a good question.
The play.
No, I think it's the demuxer, actually. And the reason is because packets typically come in the correct order. So a packet for a video frame has a PTS and a DTS, and it's a timestamp in terms of the time base. And the PTS is the presentation timestamp, and the DTS is the decode timestamp. And the problem with video is frames can come backward. So you can actually get with H264 encodes what they call B frames. You guys familiar with this at all? So H264 encodes what they call B frames, and they build a frame from the previous frame and the next frame, right? And so when you get a B frame, you can't decode it until you get the next frame. So you'll see sometimes the presentation timestamp and the decode timestamp are, like the presentation timestamp moves forward, but the decode timestamp actually will sometimes move backward. And then the demuxer is responsible for I believe, I could be wrong, is responsible for actually presenting the packets in the correct order and making sure you get it monotonically increasing PTS. The presentation timestamp is monotonically increasing.
I often see delays between audio and video where there's post-processing been applied to the audio.
Yeah, I don't know why. Yeah,
Right,
I don't know.
so
I've seen that.
The speech comes behind, and that's because they put it through a reverb or an echo effect to improve the sound quality.
Yeah, that's probably the video editor and the re-encoding side. But it used to be back in the old days when MPEG first came out. I remember getting lots and lots of videos that would slowly desync the audio and video. Mm-hmm. Like I mean, maybe they just finally worked that out. That's what all this PTS, DTS, time-based stuff is all about. Especially in the new containers and these. You actually do have access to that in the Java. I don't have any slides on that, but you can actually get the packet detail metadata, including the PTS, DTS, and time base in Java if you wanted to do something with it.
Probably not on that side.
And the other thing is that I don't care about audio. So the remuxing works accidentally because FFmpeg just takes the packets and knows what to do with them. But in my work and so far in this, I'm willing, if anyone wants to contribute audio sides to this, it only does video. So once you get to the part of the pipeline, over here, where you get even though I have the audio picture here, theoretically you can get audio, raw audio code out of that. I don't know how to handle it. I don't, and it doesn't do it in the Java side. So if any of you guys are bored, it's open source.
So that is included in OpenCV.
No.
That's not.
Nope.
That's just
No,
video.
that's also it's only video. Yeah. It is included in FFmpeg, so if you wanted to write a lot of low-level C code, you could get it. Okay. The actual structure of a media context is so what I showed you is really simple, written with convenience methods use of the media context, but you can drill in, and it's basically structured this way. You have a data source, which really is the demuxer. So it's where is it coming from and what demuxer am I going to use to demux it. But then you can have a series of processing chains with packet filters, and which will be applied sequentially. So if you add 3 or 4 packet filters, it will decide whether or not the packets actually flow through. There's really only one useful packet filter. Well, actually, there's probably more than one, but the most useful one is give me the first video stream, and I don't care about anything else. And it just drops all the audio packets. It drops all, if there's more than one video stream, it'll drop all their video streams. And then the media processors, you can define multiple media processors, but each one will take whatever packet survives the filter. They're not chained in the same way. And you can have multiple chains if you wanted to. Another code example of that. So this is explicitly defining the source, which, instead of using the convenience method, I open a chain, prefer BGR, select the first video stream, remux it to an output file. I also want to display the frames. I go back to the media context. This is like a builder. I add a second chain. I want to remux that to an output file. And go back to the media context and start the processing. So you'll notice I switched to a file here. And the reason is because I could switch these to AVI files and still use the camera, but I can't. An MP4 file has to be closed. So it actually goes back to the beginning of the file and fills in header information and trailer information. in the MP4 file. So the stream has to end, and you can't just stop it, or you'll get a file that won't play. I don't actually have an example of this, but I could stop the stream from inside of one of these lambdas by just timing it, and then the context has a stop. And if you stop, it shuts down appropriately. And so it'll close the MP4 file, like all of that stuff will happen. So, but this is, let's just see what happens here. So, about 70 seconds of video, it went through, remuxed it into two different files. If you notice that those two different processing chains, you notice the difference between those two different processing chains. Really, the only difference is I have a packet filter on this one, which says I want nothing to survive this filter except for the first video, except for whatever comes from the first video stream in the file. So timing is correct because it just remuxed it, just moved the stream over. So when I play it back in a regular player, it doesn't play, it plays it back at regular speed. But I can't hear it. Oh, that's right, I have my sound off. Never mind. You have to take my word for it. This video actually has the sound that was in the original also in the Remux file. Okay. This is something else you can't do with OpenCV, but you can with lib FFMpeg, is you can provide the source, a custom source of data. So if you wanted to play an MP4 file from memory, you could do it with this. If you wanted to write an MP4 file into memory, you could do it with this. In this case, there's two interfaces or lambdas, interfaces that you can pass as lambdas. It's a media data supplier. It'll basically, the processing chain will call you with a buffer, and it'll say, hey, give me this many bytes. And then your responsibility is to fill the buffer with that many bytes, and then return how many bytes you actually filled it with. So don't fill it with more than that, but you could fill it with less. It might call you back right away for more. But, some demuxers, like an MP4 demuxer, require you to be able to seek. So you have to provide a seek method. So it'll say, okay, we're at this position, move it to the beginning, move it to the end, move this many bytes from the beginning, this many bytes from the end. So, but there are tests, and I don't have code for this to show, but there are tests, and if you wanted to look at it, there are tests that actually load an MP4 file into memory, and then play the MP4 file out of memory. And also on the output side, we'll write an MP4 file and then write it out to disk, and then play it back, make sure that it actually works. And again, I mentioned custom output, same thing. So if you wanted on the output side, you pass it a write packet. It'll give you a buffer and tell you how much of this buffer has valid data, and then you ingest it, do what you want with it. And then if it requires a seek, it's the exact same seek interface. How are we doing?
Good. Time-wise?
You tell me what I mean? I don't know. I mean, I have encoding left, so I can go through encoding, and then I was going to walk through really quick some of the final stuff. I could skip the encoding for the final stuff if you want, or yeah.
I had a question, like, are these the only formats that OpenCV supports, or are there more formats that?
What do you mean? Oh, no. These are just examples. Yeah, these are just examples.
Well, what about the 1 hour mark? How's everyone doing? Good. I'm still forming memories.
Okay. All right.
Not always the case.
I'll do an encoding example. So here, this is a transcoding example. So I have a media context to play the media. I have a encoding context to write a file. You can do this with OpenCV without using PileCV4J. It has a video capture to read some media source and convert it into frames. It also has I think it's called a video encoder, and you can just push mats to it, and it'll write a video file. You have to tell it what the speed is. You have to do that here too. So in this case, I need some information about what the frame rate is going to be, and so there's a convenience method. I could actually read the frame rate from the media context. There's a bunch of accessors here, but I just pass the media context to this and say set the frames per second to whatever the input source is.
But could you go here? So you're actually just pulling the video off the input source and encoding it as is, it looks like. So it's basically, what transformation are you making here?
I'm not changing it.
Okay.
I have another example.
On the other hand, if you set like the frames per second to 10,
No, it would play different. Right? I mean, if I set it, I could just set it to 10, and then the resulting file, if the input wasn't 10, the resulting file would play faster or slower. Or
right.
whatever. Yeah. Yes. This is just pure transcoding. It's not doing anything with the frames. So there are cases where I don't ever do this. I mean, it's just a dumb thing to do if you can avoid it, because you lose data, you lose information. If you transcode a video, you lose information. If you remux a video, you don't lose anything. But if you decode it, and then as soon as you re-encode it, I mean, I guess it's potentially theoretically possible that you could re-encode it losslessly. You can only lose information.
Right. But that's a lossy, just like
Yeah,
JPEG.
they're not all lossy, but most of them are. Right?
Jim, we have another question on the live stream here. Does FFMpeg have to be loaded on the host machine?
Yes.
There you go.
Yes, I was going to actually bundle it like I did with OpenCV, but I never got around to it, and I'm not sure that doing that with OpenCV is the right choice either. So right now, you have to have FFmpeg libraries on your machine. You have to have the development libraries to build it, but you have to have at least FFmpeg installed on the machine to run it. That's not true for OpenCV, at least the way this is currently set up. So anyway. I could play this. Do you believe me it's going to work? All right, let's just skip that. And again, it's more complicated structure than appeared in the. If you wanted to dig in a little bit, you're going to have multiple video encoders applying to a single muxer, and then you could have custom output if you wanted to, the same way that you can, when you're remuxing.
So let's say you have two separate cameras as your source, and you're muxing them into one output. What does it end up doing? So like
You have two streams. No, you have two streams. Actually, I have an example of that. Not of two cameras, but of one camera. Here, let me show you that. Let me just go right to that.
But the two streams are completely separate, so you play them as separate streams.
Yeah, but most players, not all players, but some players, like BLC, for example, you can go video track. They're tracks. They're video tracks. Right. So here's an example where I'm creating two video encoders. They're both encoding H.264. This is the name of the video encoder to use. You can get a list of these in the FFmpeg documentation, but that's the standard one. I'm setting the frames per second to the same as the input frames per second. I'm dropping everything except for the first video stream. There's an extra step that's done automatically if you only have one of these on the first encode, which is you have to actually tell it, okay, you have to enable it. I haven't figured out, I probably could get around this, but it needs the transformation information at the time of enabling. So it needs to know the transformation information, and it needs to know how big is it going to be writing, what's the output size, what's the output dimensions of the image, and all that stuff, and the frame rate. This is another thing to note here. Process video frames can take two handlers of frames. If you pass it two, it will call the first one once. So if you need to do setup, because you don't know what size the frames are or anything like that in your processing, you can pass it 2 handlers. The first one will get called once ever. It's like an initialization one. And then the second one will be called along with the first frame and every frame after that. And the reason is it's much more, it's inside, it actually swaps which one's being called. So it's kind of more efficient. So anyway, on initialization, it's actually doing this, and all the frames are actually being played in the second handler. And the second handler is encoding the frame as it is, but it's also then flipping. This function flips it around the the y-axis. If I had 0 here, it would flip it upside down on the x-axis. It flips it around the y-axis, sends the frame to the second encoder, and then plays. So it's the output file, out3.ffmpeg or .mp4. Anyway, do I have a sync on this? It's playing slow. Huh.
What's wrong?
Huh. Nope, I didn't. Wow, it's playing really
It's
slow.
not creating any sort of, or is that image builder up there creating the window? Yeah, image display builder.
Yeah, and then it's actually displaying it here.
Okay.
And obviously it's not changing it to it's obviously not encoded correctly. There's no sync in here. That's very strange. It's playing a lot slower than I expected it to. So it's doing a lot of work. So it's going to take a minute to run. Yeah. What's that?
That is much faster.
Yeah, I guess it is going a little bit faster. It's certainly going a lot slower than it did, when I just zipped through it when I was doing a Remux, right? And the reason is because it's doing doubling. It's going through that pipeline, but it's actually going through 2 separate encoders. So it's really computationally intensive. And it's blue because I didn't convert it to BGR. All right. Now let's play the output file with VLC.
Matrix look.
Okay. Two tracks in the same video file. One's flipped around the y-axis.
How many can you throw in?
You could probably throw a ton in if you want. I mean,
Like DVDs will have hundreds of video tracks.
yeah. I mean, it's a MP4 file which supports multiple video tracks. So I don't know if there's a limit.
The format itself doesn't define it. Is it like 256 or something?
It might. I don't know. I mean, I don't know how many video streams. The containers have all their own different. Every different container has different.
At least for DVDs, I don't think there's much of a limit because like when they were in like the copy protection wars, they would throw in like hundreds of thousands of like out of order. Like, they basically have like a couple hundred chapters, a couple hundred titles on the DVD, all which had the exact same video stream in different order. And so when you were like trying to rip the DVD, you wouldn't know what to get. But like they had like the flag set up just right so the DVD player would figure it out. This tricked people for what, like 30 seconds?
Yeah, exactly.
35 seconds. I mean, it was real. It lasted like, but they kept doing it.
Yeah, yeah. So
You were bootlegging?
No, I'm using my legal entitlement to format change to put on my Roku.
So you do have to know a little bit about what you're doing because the different container formats support different encoding schemes. Like you can't put certain streams inside of certain containers. Like I don't know. AVI is pretty versatile, but I don't think you could put an MJPEG stream inside of an MP4 file. Like it has to be H.264 or H.265. Right? So if you try it, you'll get an error if that won't accept it. So on the encoding side, kind of walk through this. There are more options you can set. Like these are all well documented in the FFMpeg documentation. You can add codec options. I know I'm specifically using the lib X264, so I know what options I might be able to pass to this if I want to tune the encoding. I just did that. Okay. So because we started with a traditional computer vision algorithm, I'll end with a more modern one. Unfortunately, all the modern ones run better in Python than anything else. So there is a part of PileCV4J is libPython. And the whole point of this is to you write a small Python script, and it passes images to that back and forth between Java and the Python without copying. But you have to write a small chunk of Python code that
Where's the Python code running?
in Python.
But you can't, if you're doing
It's in the same process space. So the mats
It's like
are in C in native memory.
So it uses JNI
So-
to wrap Python also.
It actually uses JNA, but you might as well say JNI. This is almost the same thing. But
And for the members of the audience that don't know what JNA is,
JNA is dynamic JNI. It's
so it's like a shared library instead of a static library.
it's a shared library, and you don't have to compile the bindings. You don't have to compile you don't have to generate the bindings. You just basically declare a static native method, and it tries to find that. It says and then you load a library, and it binds that method to that library dynamically. And so all of this stuff is written the native side bound to Java using JNA instead of JNI. But OpenCV is available in Python, and it's available in Java, and the image memory sits in off heap. It's not in the Java. It's not managed by Java. It's just sitting in native
I
memory.
get that. You're loading in the Python interpreter.
In the same process space as the Java. and yes, and it basically passes the OpenCV mat to C code, which actually converts it to a NumPy array. And then on the Python side, I'll show you. So create a Python handle, you add a module path, you add parameters that you're going to pass to a Python function, and you invoke a Python function. That Python function has to do a couple things. It gets past, if you notice, it gets past the Java handle. So it gets past the actual Python handle. What's that?
So you wrote this library to?
Yeah. And I actually originally wrote it so that you could call any Python function you wanted, but it's slow as hell because it kept going back and forth. So instead what it does now is the Java and the Python run independently. So you have to write the snippet of Python code so that it goes into a loop and pulls for images. And it's kind of just a little bit of this is basically just a little bit of a handshake between the two. So and then you just pass the images back and forth, and then it runs a whole heck of a lot faster because you're not restarting the Python every time you want to like execute a function on it. And it just runs. The Python's always running, the Java's always running, and they're just passing an image without copying it between the two systems. And this is how basically that, I'll run it again, but this is how the object detection that was running when you first came in worked. It's running YOLO v5 on Pytorch. Now, it's not a general purpose call Python from Java, because it's specifically meant to pass images back and forth to have AI models run on it. Keep them It's because he's closest to the camera.
Have you looked at Growl at all?
No, I've never even heard of it. What is it?
It's Growl VM. Oracle makes it, and you can run different languages on the JVM, I guess. But I think Python, I think Python as well. We're using it now for, it's a replacement of Rhino. So we did Rhino and then did Nashorn. This kind of allows you to.
It's not like Python, is it? Because it's not like it runs on the virtual machine.
No, it's its own thing.
Oh, so I can't run. So I had to set this up by creating a Python virtual environment, installing Pytorch, loading a ton of Python requirements to run Pytorch, and then I started Eclipse in the Python environment so that I could. So this is literally calling.
They're in the JVM. They're in the JVM. They're in the VM.
They can run a JVM within the Growl environment, which they'll do if they can't compile it to native.
That's different than what you said.
Yeah, so this is
So we have a question online.
But yeah, go ahead.
Have you ever tried this with a Python JIT like Numba?
I'm not familiar with that. Is that like Jython, where it basically compiles to Java bytecode? It compiles Python to Java bytecode, because that won't work. Because I need Pytorch, which is basically written in C, with and meant to be used from Python, and uses the GPU.
It's a question from Mike, so he might just be jerking.
Oh, okay. Is he the only one on?
No, that's fine. Yeah, he says it's an actual just-in-time compiler, numba.pydata.org.
Oh, he's now a Python expert. So, but yeah, this is there.
No, Mike. Sorry.
This is there if you want to use it. So the steps are a little bit complicated since the Python code takes the YOLO. This is typical of neural networks. They take a fixed aperture, like the image has to be an exact certain size. So this resizes and letterboxes the image. It sends them out to Python, waits for the results to come back, and then parses the results, because the results also come back in a mat where each row is an object detection. It's a matrix basically that comes back. It's the box is 4, and then probability and the class. So whether it's a person or a chair or whatever is the class, and the probability you see the display, and then the box is the 4 corners of the box. So anyway, it parses the map into a set of records in this case, and draws them using straight. This is straight OpenCV. Draw into an image a rectangle and put the text at a certain spot. This is the culmination of everything now. I could probably do an encoder and write this out to a video file, and I save it off if you wanted to keep it's for some reason, but whatever. Okay, that's about it. I think I have one slide left. Okay, just to wrap up, there's several other miscellaneous projects. There is libIPC. So this is literally an IPC implementation.
What I was actually thinking.
It's shared memory. No, it's not how I did it.
Yeah, no, it's
But
not how you did it.
This is available,
Yeah.
and it's also built around mats. So it's meant to pass a large chunk of data between two processes using shared memory. And I think I got it to 8,000 images a second between two processes. So using POSIX. This is slow as hell. But it has 3 different implementations, so you can decide which one to use. So I don't know if you guys are familiar with shared memory, but IPC shared memory. There's not a library in Java for it. Now there is. If you want to use it, I couldn't find it.
Yeah, years and years ago, so I can't remember. It was something to do with the byte buffers. I showed an example of using a map byte buffer to shared memory.
You could probably do that, but you have to somehow create the shared memory using IPC system call.
Yeah.
Right? So you have to use, shem grade, shem get, shem at, whatever. That's the system 5 version of it. But the POSIX one is shared create, or I don't remember. I only did this a month ago. I don't have that good of a memory. So, IPC library meant to pass images between processes. libtf is a very lightweight wrapper around TensorFlow's Java bindings, just to tie mats to TensorFlow. I hate TensorFlow, but I could have kept that demo in Java instead of using Python if I used it. But TensorFlow is just another deep learning framework to run AI models on. libnr, some miscellaneous stuff. libnr is this is why it's PileCV4J. It's just a numerical recipes in C. A couple methods may be useful. I don't know, primarily Powell's method for minimization. And libtracking is a wrapper and abstraction around OpenCV's various multi-object trackers. Mike actually wrote it. So it's got optical flow. It's got tracking based on optical flow and tracking based on Kalman filtering. But it's a way that if you use OpenCV, those APIs are totally different. So if you want to use optical flow, it's one thing. If you want to use Kalman filters to do tracking, it's completely different. So this kind of pulls them together into a single tracking abstraction. But it's really OpenCV under the covers. So, and that's it.
Are there any Onyx runtimes available?
Who's asking that? You're welcome to tie one in, Mike. It's still open source.
We will accept your pull request. All right. Well, thank you very much.
Sure.
I'm going to end the broadcast, so thank you all for attending.